Hi guys, welcome back to another exciting day of mathematics. We are going to continue our discussion of rotations specific to symmetry, which I know is something you've discussed since probably as early as elementary school with snowflakes and butterflies and things like that. But I want to look specifically at a little more detail. Rotational symmetry is also known as radial symmetry, and the concept is simple, right? When you can rotate a figure around its center and it looks the same. Of course, that rotating it by an angle less than 360 and greater than 0, because every figure can be rotated by 360 and look the same. But for instance, if I look at this this triangle here and I pictured this being the center of rotation, you can see how if I rotate around in this direction, when this point, I'll call it A, lands here, then this point would land here, and this point would land back where A was, and it would be the exact same image. And you can kind of see this. I have several examples. And so first let's talk about some vocabulary. So we say that the order is the number of times that I could rotate it. So for instance, the example I showed here, if I rotated it around this many, that would be 360 divided by 3, right? That would be a 120 degree rotation. If I rotated the entire figure by 120 degrees, it would look the exact same. But notice that if I tried a 240 degree rotation, right? If I, instead of doing 120, sorry, I do want to call this A. If I rotated by 240 degrees, point A would go all the way around and land here, right? And this point, let's say I called it B, would actually land exactly where A is, and this point C would land all the way where B is. So that would work as well. It would look the exact same. And then of course 360 would take me back again. So the idea is we would say that this figure has an order of 3, right? Because I have basically 1, 2, 3 rotations to get back to the exact original image if I were to actually name points. We can look here at this next figure. If I had this, whatever, I call it A or X or whatever point you want, P, then I could have 1 rotation, 2 rotations, 3, 4, 5, and 6 to get back to where I started. So the order would be 6. And notice, I know I picked that point, but it could be any point on here, right? Whether I chose that one. If I went around 1, 2, 3, 4, 5, and then 6 to get back where I started, right? It's any point. It doesn't matter which one. And so we can scroll over and look at a couple other examples. I have a tire and a flower. Both of these have order of 5. You can see here, this would be 1. Black is not the best color to use, probably. 1, 2, 3, 4, 5. Same thing here is 5. But I do want you to notice, well, we'll go back to something else later. So one other thing that I'd like to point out is something called the angle of rotation, which you can see at the bottom of the screen here. Because go back and, like I said, notice that like if I go to this second image, for instance, there's 6 different rotations. We know 360 degrees is an entire full rotation, right? So if I have 360 total degrees and there are 6 equal rotations that I can go through, then 60 degrees is the smallest angle by which I could rotate this figure so that it would be identical, right? And that we call the angle of rotation. It's 60 degrees. Right, so if I rotated 60p prime would be here, and every point would be 60 degrees away. Now, like I said earlier, 60 is not the only angle that I could rotate by to get a congruent image, right? I could rotate by 120 degrees, and so let me actually clean up some of my writing because there's a lot going on here. Okay, so notice if I were to rotate by 120 degrees, P would go to here, and everything would be great. If I were to rotate by 180 degrees, P would go to here. If I rotated by 240, it would go to here. So all of the possible angles of rotation that would give me the same are multiples of my smallest angle. And so I do want us to understand that how I find the angle of rotation is simply by taking 360 degrees and dividing by the order, right? N equals the order. So whatever the order of rotational symmetry is, I can find the angle of rotation by dividing 360 by it. Okay, I want to take a look at this statement at the bottom here that says some of these figures above have reflectional symmetry and some do not. They all have rotational symmetry. So if you look at this triangle, I noticed that if I had a line of reflection right here and I reflected across it, it would be the exact same image. And I noticed I could do it the same thing over that line and over, whoops, that's a pretty terrible line. But you see what I mean? There are three of them here. The same thing would work for this second image, right? I have some different lines of symmetry, one there and one there and one here, and I can keep going. There's 4 and 5 and 6 of them. But then if I look at these two on the right, the same thing may or may not happen. So notice if I did try to draw a line, say right here, straight down, then it would be symmetric. Right, it would land on itself, and there are some others. But in this flower, it would not, right? Because of the way you can see kind of this tail, when I flip it, would be over here, and it doesn't exist over there. So I want us to recognize that just because there is rotational symmetry doesn't mean there is reflectional. For instance, just something as simple as an S. I could rotate this around here and it by 180 degrees and it would look identical, but if I tried reflecting across this or across this, it wouldn't work. So that takes us to something special. I want to talk about polygons real quickly. Of course we know what polygons are, but regular polygons are ones that have all sides and angles are congruent, right? They're equilateral, all their sides are the same length, and they are equiangular, are congruent. But they have an interesting property that they all have both reflectional and rotational symmetry. So you see here I have a pentagon. You can kind of see the rotational symmetry here. If I rotated by 360 divided by 5, which is 72 degrees, then it would be the same figure, right? It has that rotational symmetry, but it also has reflectional symmetry, right? I could draw a line straight down, basically a line from any vertex through the midpoint of the opposite side, and it's going to give me some reflectional symmetry. Same thing here with my hexagon, right? I have these different lines of symmetry. I can also draw them through the midpoints of the sides, and I'm doing a pretty rough job here of drawing these lines, but I also, again, notice that I could be rotating. I've got several figures here, an octagon, a triangle, and we can kind of see, right, this is always happening. I have these lines, but I also have the ability to rotate, and so again, the angle of rotation is always going to be equal to 360 over n. And notice that the number of lines of symmetry is always equal to n. Okay, so there's this constant relationship between the order, right? Because the number of lines of symmetry is the order, and that is related to the angle of rotation each time. So you may be asked to answer something like, what is the order of the rotational symmetry of this figure? So in this case, my order would be 3. Or you might be asked to answer, like, what is the angle of rotation? which of course in this case would be 360 over 3, which is 120 degrees. And of course you could be asked to draw any lines of symmetry, which is going to involve our vertices generally and midpoints of sides. So we could be asked any of these types of questions, and we're going to investigate these a little further in class and hopefully do some fun stuff with it.